Okay, in this video I'm going to do some motion and forces from Unit P2 and it's topic 3. Okay, right, what I'll do is I'll split this video into two probably. I'm going to do something on distance time graphs and velocity time graphs and how you interpret gradients of the lines, how you calculate them, how you find the distance travelled from the graphs, etc. And I'll leave, more than likely depending on how long it takes, I'll leave Newton's laws and forces for another video. Okay, so let's make a start. Right, firstly we can use distance time graphs and velocity time graphs to be able to show the motion of an object against time. So let me just start with a distance time graph. Distance time. Okay, now if I drew a line that looked like this, what that would show is an object was moving at a constant speed. Okay, and we know it's a constant speed because for every amount of time that we go across, equal amount of time, you can see that this object, or it should be, that this object is travelling the same amount of distance for each amount of time. Okay, so the thing is moving at a constant speed. Now if I drew a line like this, distance time straight across, well, as time is going by, the distance of this object from some start point isn't changing. So this is constant speed, and this one is stationary, still stopped. Okay, a line like this, again a distance time graph, a line like this shows that an object is speeding up because for every amount of time that we're going past, you should be able to see the thing, whether it's a car, a person, a motorbike, whatever, starts to cover more distance for every amount of time that we go across. And so using that sort of thinking, if we do something like this, we'll see that for every amount of time that we jump across, could be a second, could be 5 seconds, doesn't matter, and I'll just do another one to show you, we can see that at first in that amount of time the thing, whatever it is, went that far, then a bit later in the same amount of time it didn't go quite as far, didn't go quite as far, didn't go quite as far. That's because it's slowing down. Okay, now if I draw those four, or if I draw 4 velocity time graphs, you'll see that sometimes it's easy to get confused. You can think, well, that looks like constant speed on this graph, but actually on a velocity time graph it's totally different. So if I just draw those 4 graphs again, those 4 sets of axes, we've got velocity time. Right, a line like this. This time, because velocity, for now, velocity is just like speed. Okay, so this axis no longer tells us distance, but tells us actually how fast something is going. So this line tells me that at the start, when the time, so this is the time axis, when time was 0, the velocity was 0. It meant it wasn't moving. But as time went by, the velocity of this object, in other words the speed of it, started to increase. Okay, so this thing is speeding up, not like before where on a distance time graph that would mean constant speed. This means speeding up, and actually this is constant acceleration. Okay, right, a line that goes straight across like this, this isn't like on a distance time graph where straight across meant stationary. This graph is steady speed, so in other words constant velocity. Okay, if I drew a line that looked like this, at the start when the time was 0, whatever it was that was moving really quickly, it had some velocity. Then as time went by, the velocity got smaller and smaller and smaller and smaller. So this is a constant deceleration. Okay, in other words, slowing down. And I'm not going to put anything on the last one. Right, okay, so if I just put these in front of you again, I'll leave them there for a second so you can have a little look at them. I've wrote speeding up there, that's actually acceleration, slowing down is deceleration. Okay, and that one. Right, so if we get down to looking at some calculations now, if we consider a distance time graph first, if we've got time, distance, let's put some numbers on this, 1, 2, let's go 2, 4. Now I know it's not perfect, but you'll be able to see the way I'm working here. If I drew a line that went like this, if I had to use this graph, it's a distance time graph, to determine the speed of this object, and that should be a straight line by the way, then what I need to realise is that speed equals distance divided by time. Okay, so the distance the object moves, well, I could go from the start to the end. Okay, let's go that far. And I could say, right, the distance travelled looks like 8 metres. It's gone from 0 metres to 8 metres in a time of 6 seconds. So 8 over 6 is 1 1/3, so it's 1.33 metres per second. Okay. Now, I could have gone like this. I could have said, well, let's just try and find the speed to this point. So what's the speed in that section there? Well, same equation. Speed equals, this time, the distance between this point and this point is, it's gone from 0 metres to 4 metres. So that would make this number a 4. So we'll do this. And it took between 0 seconds and 3 seconds, that's 3 seconds to do that. So 4 over 3 is again 1.33 metres per second, which is right. Because if this thing is a straight line, that means it's constant speed. So it wouldn't actually matter which points I took, as long as I took the correct change in distance and the correct change in time, then I'll be able to calculate the speed. Okay? So all your questions that you get on calculating speed from distance time graphs will be done in exactly the same way. And just for completeness, I could even say, well, let's go between this point and this point. Well, how far does it travel between there and there? It goes 4 metres, between 4 and 8, so that's a jump of 4 metres, and it took 3 seconds, so again, that will be 4 over 3, 1.33 metres per second. Okay? Right, that's how you calculate speed from a distance time graph. Now, just to, I won't do this in numbers, but if I was to compare the speed of this object to the speed of an object like that, you should be able to see that this one is actually a faster object than this one, because it's covering a great amount of distance in a short amount of time. So actually, you calculate the speed of an object on a distance time graph from the gradient of the line. The steeper the gradient, the faster the object is travelling. Okay? Right, let's go to velocity time graphs. Okay, same thing. I'm going to go velocity, time, 0, 1. Okay, just so it's a bit different, I'll go up in tens. Okay, Now what I'll do here is, I'll do 2 lines, so let me just try and put that there like that. So this shows that an object starts stationary, not moving. Then, remember this is a velocity time graph, so this is actually how fast the object is moving. And we could say that's in meters per second, and we could say that's in seconds. So it starts off at 0 meters per second, then accelerates, so that after 2 seconds it's travelling 50 meters per second, and then between 2 seconds and 6 seconds it travels at a constant velocity, which is 50 meters per second all the way across. Right. So you can be asked to do 2 things on a velocity time graph. The first one is to calculate the acceleration of the object. So I'm going to call these 2 different stages. I'll call them stage 1 and stage 2. Right. Now in stage 2, you can see that the object isn't accelerating. It's not speeding up, it's not slowing down, so there's no acceleration at all. So if you got a question like this, and it looked like this on a past paper, or sorry, on an exam paper, and it says, calculate the acceleration during stage 1. Well, you would need to say, well, acceleration is, and the formula is, change in velocity, I'm just going to put change in v, over the time taken. Okay? So, much like we did just for the distance time graph to calculate the speed, what we need to do is we say, right, let's pick 2 points on the line. I'm going to choose the start and I'll choose the end because it looks easy. Right, what was the change in velocity between there and there? Well, this is the velocity axis. So, by how much did the velocity change? Well, it changed, went from 0 all the way up to 50. So the change was 50. How long did it take? That was at 0 seconds, that was at 2 seconds, it took 2 seconds. Okay, so the acceleration is 25 meters per second squared, and that's the unit. That squared doesn't actually mean that you square anything, it's just the unit. Okay, 25 meters per second squared was the acceleration. That's the first thing you can be asked to do on a velocity time graph. So, again, the greater the gradient, the larger the acceleration is. And obviously, the lower the gradient, the smaller the gradient, the smaller the acceleration. Now, I'm just going to get rid of this to give me a bit of space. The second thing you can be asked to do on a velocity time graph is, I could say to you, right, well, how far does the object travel in total? So, if this goes all the way to 6 seconds there, in that 6 second period, what's the total distance the object travels? And the way to do this is, you've got a triangle basically, you need to split this up, because the distance travelled, right here, distance travelled is equal to the area underneath the line. Okay? So if I want to find the distance travelled, I've got the area underneath section 1, the area underneath section 2. This is a triangle, so I have to calculate that area, then I have to calculate that area, and I add them together. Okay, so section 1 is going to be half times base times height, which is a half times 2 times 50. So the area equals, that's a half times 2, which is 1, times 50, which is 50 meters. And then this one, because this is a rectangle or a square, we've got base times height. So area equals, now this is a classic mistake. You might look at this and go, right, base, and you just look over here and you go 6 wide. It's not, is it? It's obviously not. Between 2 and 6, we've got a base there of 4, 1, 2, 3, 4. So base times by height, again, height of 50, which will give us an area of 200, obviously. Now, this might be, I've just realised this might be slightly confusing, because I'm using the word area, then I've got 50 metres. I'm not using something which is, you might recognise from maths, area, you're going to put a unit of metres squared. Now, it probably would make more sense if I wrote distance there. Dist. Okay. Now, what I'm doing is I'm multiplying something on this axis that's got units of seconds by something on this axis which has got units of metres per second. So if you multiply metres per second times by something with seconds, it will give you something with units of metres. Okay, that's where I'm getting this from. So let me just get rid of that. So if I add this distance of 50 metres to this distance of 200, I can say the total distance travelled would be 250 metres. Okay, and that's it. So to round up quickly, different shape graphs. You've got distance time graphs and velocity time graphs. There's your distance time graphs. Make sure you know those shapes. Make sure you know that they're different and what they are. And make sure that when it comes to a velocity time graph, that you know how to calculate the acceleration from the gradient and how to calculate the distance travelled from the area underneath the line. Okay? Right. Now, the video that goes with this will be about Newton's laws to explain motion using forces. So after watching this, you might want to move on to that video. Okay, cheers.